Hi team, welcome back to General Chemistry Chapter 4, Compounds and Stoichiometry. We're going to start off with 4.1, Molecules and Moles. So molecules are a combination of two or more atoms held together by covalent bonds. Can be of two or more atoms of the same element, like N2, so you have two nitrogens, which is a pure element, or can be of two or more atoms of different elements, like CO2, so you have a carbon and oxygen, and that makes a compound. Ionic compounds do not form true molecules because of the way in which the oppositely charged ions arrange themselves in the solid state, formula units like NaCl. And then we have our molecular weight, and that's the sum of the atomic weights of all of the atoms in a molecule. And the units are AMU, which from chapter 1 we know is atomic mass unit per molecule. So I just have an example here, and it's asking, what's the molecular weight of SOCl2? So we're going to write 1S, because there's one sulfur, so 1 mole of S times the atomic mass unit, which is 32.1. This AMU is also the molar mass, so if you look at the periodic table, whatever the molar mass of that element, that will be your AMU. So 1 mole of sulfur times its atomic mass unit, you will get 32.1 AMU as your final answer for sulfur. And then we have 1 mole of oxygen as well, so we do the same thing, 1 times 16.0 AMU, and your answer should be 16.0 AMU. It's final answer because we're going to carry those units over. Now for chlorine, since it's Cl2, we're going to have 2 moles of chlorine. So it's 2 times 35.5 AMU is equal to 71.0 AMU. And we're going to add all of that up. We're going to get 119.1 AMU, and that should be your final answer. So that's how you calculate the molecular weight. Moving on to mole. So this is the equation that the textbook gave, which is moles is equal to mass of sample in grams over molar mass, grams per mole. Or you can write it as N is equal to M over uppercase M for molar mass. So just a side note, 1 mole is equal to 6.022 times 10 to the 23 and 1 over mole. And that's the Avogadro's constant, which can also be written as Na. And 1 AMU is equal to 1 gram of mole, like we said before. So whatever the molar mass, that will be the same number for atomic mass units. So I have another example here for us. So it says, how many moles are in 9.53 grams of MgCl2? So the first thing we have to do is find the molar mass of MgCl2, so the overall compound. And we're going to go with 1 mole of Mg plus 2 moles of chlorine. So it's going to be 1 times the molar mass, of Mg, so that's 24.3 grams per mole, plus 2 times the molar mass of chlorine, which is 35.5 grams per mole, and we're going to add all of that up. We're going to get 95.3 grams per mole for the whole compound. And then number 2, we're going to solve for the number of moles. So we got N is equal to M over capital M, like I said before, and N is our moles. This lowercase m is mass, the uppercase M is molar mass. So it's going to be 9.53 grams over the molar mass of the whole compound, so that's 95.3 grams per mole, and we're going to get 0.10 moles of MgCl2, and that's our final answer. So moving on to equivalent weight, it's the measure of the mass of a substance that can donate one equivalent of the species of interest. The way we write this is gram equivalent weight is equal to molar mass, which is grams per mole, over N, which is the number of particles of interest. So I have an example down here. It's asking, what is the gram equivalent weight, so GEW, of sulfuric acid? Now it's important to know how to write out sulfuric acid. So it's H2SO4. So the first thing that we do is find the molar mass of sulfuric acid, and that would be 2 moles of H plus 1 mole of sulfur plus 4 moles of oxygen. And now we plug in the molar mass quantities for each element, and we should get a total of 98.1 grams per mole for H2SO4. And then moving on to step 2 in answering the question, it's calculate the GeW, which is the protons, and that's hydrogen ions. So the number of protons in H2SO4 is equal to moles, and that's equal to 2. So GeW, we're going to write out the equation. GeW is equal to molar mass over N. And because H2SO4 has 2 hydrogens, so N is 2, we're going to go with the molar mass that we calculated before. So it's 98.1 grams per mole over 2 hydrogen ions. That should give us a total and final answer of 49.05 grams per mole of hydrogen ions. And that's how you answer that. Moving on to equivalence. They are moles of species of interest, like we said before, and they're often seen in acid-base chemistry. So you'll either have hydrogen ion or hydroxide ions, and in oxidation reduction reactions. So this is an important equation to be aware of. It says equivalence is equal to mass, which is grams, over GeW, which is also grams. So the grams and grams cancel out, and equivalence will be unitless. Moving on to normality. Normality is usually written with a capital N, and that's the ratio of equivalents per liter. So 1 N of hydrogen ion is equal to 1 mole per liter. It's related to molarity, the measure of concentration. So the molarity, which is a capital M, and that's mole per liter, that's the units, will equal to normality, which is N times moles per liter, and N is equal to the number of particles of interest. And that's the equation for figuring out normality and molarity. Just know that you can move this equation depending on what you're being asked of. So just keep this equation in mind. And I have an example right here, and it's asking, what is the normality of a 2 mole of MgOH2 solution? So we're going to start with writing out the equation where molarity is equal to normality over N. We're just going to rearrange this equation here because we want to solve for normality. So normality is equal to molarity times N. So N is equal to, so capital N, normality, is equal to, we're given the 2 moles, we're given the molarity, so it's going to be 2M times, and when we look at the equation, it's MgOH2, so there's 2 moles of hydroxide ions, and we're going to go 2 of OH, and we should get 4N of MgOH2. Next we have 4.2, where we talk about the representation of compounds. We touched on Vesper theory before and Lewis dot structure, and another one is line structure, where we'll go over it more in detail in organic chemistry. So we're going to talk about the law of constraint composition, where any pure sample of a compound will contain the same elements in the same mass ratio. For example, every sample of H2O will contain 2 hydrogens and 1 oxygen, which makes sense if we think about it. So the empirical formula is the smallest whole number ratio of the element in a compound. So ionic compounds like NaCl, CaCO3 will only have EF. Whereas the molecular formula, either the same as or a multiple of the empirical formula. It gives the exact number of atoms of each element in a compound. So in the example below, I have benzene here, the benzene ring, and the molecular formula for that would be C6H6, because that's the exact number of atoms present in that benzene ring currently. However, for the empirical formula, we're going to find the smallest whole number ratio. So if we divide C6 by 6, we're going to get 1, so 1 carbon, and H6 by 6, we're going to get 1 hydrogen. And that's the empirical formula for benzene. For glucose, we have the molecular formula of C6H12O6. because that's the exact number of atoms that are present in glucose. However, if we were to simplify this, we would take C6 divided by 6, we would get 1 mole of carbon, H12, and we can't divide H12 by 12 because we have to divide everything by the same number to get that exact ratio. So we can divide H12 by 6 as well, and we should get H2. And we divide O6 by 6, and we should get 1 mole of oxygen. So the empirical formula comes down to CH2O. And I have an example here. So what's the EF and MF, which represent empirical formula and molecular formula, for a carbohydrate that contains 40.9% carbon, 4.58% hydrogen, and 54.52% oxygen, and has a molar mass of 264 grams per mole. So the first thing we want to do is determine the number of moles for each element. And I have simplified an equation here where it's moles of X. So X is any element. So we're going to take the percentage, make it into a decimal number. So we have to divide it by 100 times the molar mass of the compound and divide the whole thing by the molar mass of the element X, which is grams per mole. So we're going to start off with moles of carbon, and we're going to convert the percentage that we were given, which was 40.9%, and make it into a decimal value. So it comes down to 0.409 times the molar mass of the whole compound, which is 264 grams, and we're going to divide that by the molar mass of carbon itself. So that's 12 grams per mole. When we equal this whole thing out, we should get 9 moles for carbon. Moving on to the moles of hydrogen, same thing, we're going to convert 4.58% into a decimal value, so that's 0.458 times the molar mass of the whole compound, which is 264 grams, and divided by the molar mass of hydrogen itself, and that's 1 grams per mole. That should give us 12 mole. And for oxygen, same thing, and we should get 9 moles for that. So that's our molecular formula. We can write it out as C9H12O9. And for step number 3, to find the empirical formula, divide by a common integer value. So like I said before, we just have to look at what the numbers are divisible by, and they're all divisible by 3. So we divide that by 3. We get C6H4O3. We just look at it once again and see, can we go a bit further? And we can't go any further because then we risk losing whole number values. So we're going to stick to that, and that's our final empirical formula value. Moving on to percent composition is the percent of a specific compound that is made up of a given element. So the equation that the textbook gives us is percent composition is equal to the mass of the element in a formula over the molar mass times 100%. So an example that I have here is, what's the percent composition of chromium in K2Cr2O7? And we have to look for chromium, so that would be the Cr. So the first step we do is find the molar mass of K2Cr2O7. So we got 2 moles of K plus 2 moles of Cr plus 7 moles of oxygen. We can fill in the molar mass for each element and get a total value of 294.2 grams per mole. And then for step 2, we calculate the percent composition of chromium. So percent comp is equal to 2 times 52 grams per mole, and that's our molar mass for chromium, over the molar mass of the whole compound, that would be 294.2 grams per mole, times 100%, and we get the total value of 35.4%, and that's our final answer. And then we move on to 4.3, where we talk about the types of chemical reactions. Here we have the combination reaction wherein 2 or more reactants combine to form one product. So in the example, we have 2 moles of H2 plus O2 and 2 moles of H2O. So we're going to put A underneath H2, B underneath O2, and C underneath H2O. That's a good way to keep track of the kind of reaction it is, to see that A and B combine to make C, and that's how you know that it's a combination reaction. Moving on to decomposition reaction, when one reactant is chemically broken down into two or more products. And the key word here is chemically. So we know that some sort of energy is applied. It can be heat, it can be electricity, it can be force, pressure, anything put into the system to make sure that the two elements come apart. So in this example below, we have 2 moles of HGO, and the little triangle on top of the arrow represents heat. And then that breaks the molecule into 2 moles of Hg and 1 mole of O2. Then the next one we have is combustion reaction, and that's when a fuel and an oxidant, usually oxygen, will react, forming the products H2O and CO2. So the key thing here to look out for are the products. So we have to look for CO2 and H2O, and for the reactants, we'll have to look for the oxygen that's gonna ignite the fuel and keep it burning. And the fuel here is CH4. However, it can be any carbon-hydrogen molecule, because carbon and hydrogen are most common fuel molecules in combustion reaction. Next, we move on to the single displacement reaction. That's when an ion of one compound is replaced with another element. So here we have an example, which is Cu plus AgNO3, which makes Ag plus CuNO3. An easy way to determine the kind of displacement this is to write A under Cu, B and C under the compound. So B would be Ag and C would be NO3. After the arrow, what we want to do is flip A with B. So B would be Ag plus CuNO3, because B and A, the two elements, were flipped. So that's single displacement. Moving on to double displacement, and that's when elements of two different compounds trade places with each other to form two new compounds. And we have an example of CaCl2 plus AgNO3, which would make CaNO32 and AgCl. So under Ca, we would write A. Under Cl2, we would write B. Ag would be C, and NO3 would be D. So what we want to do is, once we've identified the A, B, C, and D, we will take B and D and make them flip places with each other. So the final answer would have A with D plus C with B. And that comes down to CaNO32 and plus AgCl. And that would be your double displacement. Next we have is a neutralization reaction, in which an acid will react with a base to form salt and water. So in our example here, we have HCl plus NaOH. So HCl would be the acid, NaOH would be the base, and that would create salt, which is NaCl, plus water molecule. And these are the type of reactions that we need to know for the MCAT. So moving on to 4.4, balancing chemical equations. So balance equations are determined using the following steps in order. And number 1, we want to balance the least common atom. Number 2, balancing the most common atom, and this is usually your hydrogen or oxygen. And then number 3, we want to balance the charge at the very last, if there is one. So here's an example. Balance the following equation, C4H8 plus O2, which will create CO2 plus H2O. Just right off the bat, because we have CO2 and H2O in our products and oxygen as a reactant along with a carbon-hydrogen molecule acting as a fuel, we can conclude that this is a combustion reaction. So our first step would be to find the least common atom, and that's carbon. So we want to balance the carbon. We have 4 on the reactant side, and when we look over to the products, we have 1. So we're going to put a 4 in front of the CO2 to balance out the carbons. And then step 2, we want to balance the most common, which are our hydrogens and oxygens. So when we look at the left side, we have 2 moles of oxygen and 10 moles of hydrogen. And we look to the right side, and we can see that the H2O has 2. And to make it 10 to equal the left side, we multiply the 2 with the 5 to get 10. So left is equal to right. Now that we have carbon and hydrogen that equal on both sides, we're going to move on to oxygen. So from before, the reactants have 2 moles of oxygen, and on the right, now that we have 2 moles of oxygen and CO2, we're going to multiply with that with the moles in front of, so that's 4 times 2, plus the 1 mole of oxygen times 5 with the water molecule, and a total for that should give us 13. Because the reactants is 2 and products is 13 for oxygen, what we have to do is look back at the reactants and put 13, so both sides match each other, but because it's O2, we have to do 13.2, which gives us a 6.5, and we can't have that because we can't have decimal values, we need whole numbers. So to get rid of that decimal value, we're going to times everything by 2. So you get 2 of C4H10 plus 13 of O2, which makes 8 CO2 plus 10 H2O. And now when we look at the values for each, they all match up, so left side is equal to right side, and the equation is now balanced. Moving on to 4.5 applications of stoichiometry. So the example given here is how many grams of calcium chloride, which is CaCl2, are needed to prepare a 71.7 gram of silver chloride according to the following equation. So they've given us the equation, and the first thing we want to do is to check if it's balanced. Once we do that and we're all in the clear, we're going to move on to molar mass for CaCl2, which is 111 grams per mole. Then we get the molar mass for AgCl, which is 143 grams per mole. So we come down and write grams of CaCl2 because that's what we're trying to find. We're going to write the mass of AgCl because that's what we're given over the molar mass, which is 143 grams per mole. So our goal here is to cross out AgCl. And because in the equation, we know that it's balanced, we have 1 mole of CaCl over 2 moles of AgCl. So the AgCl grams cancel out and the moles also cancel out. So the units so far that we have are just mole of CaCl2. So we take that and we times it with 111 grams per mole for CaCl2 that we have from before. And when we multiply it all together, we get 27.8 grams of CaCl2 because that's what we were trying to get. So just to recap, we work in a way where we take out the units for each and we go from AgCl. We cancel out the grams in the first 1/3 and then the moles of AgCl between the 143 moles of AgCl to the 2 mole of AgCl. Because the mole is a denominator in the value of that's in the denominator of another equation, that mole goes to the top. So the top and bottom cancel out. And then the mole of CaCl2 cancel out with the mole of the 111 grams per mole. So our value is grams. And the common conversions used in stoichiometry include 1 mole of any ideal gas at STP is 22.4 liters, and 1 mole of any substance is equal to the Avogadro's number, which is 6.022 times 10 to the 23 particles. And it's molar mass in grams from the periodic table. Moving on to limiting reagent. The reactant will be consumed first in a chemical reaction, and the other reactants present are termed as excess reagents. All comparisons of the reactants must be done in units of moles. So we have another example here. So if 27.9 grams of Fe reacts with 24.1 grams of sulfur to produce FeS, what would be the limiting reagent? How many grams of the excess reagent would be present in the vessel at the end of the reaction? So they already said that the balanced equation is Fe plus S is equal to FeS. So we don't have to worry about balancing it again. And then we move on. So our first step is to determine the number of moles in each reactant. So we go Fe is equal to 27.9, which is already given, grams over 55.8 grams per mole that we can find from the periodic table, and that gives us a 0.5 mole. We do the same thing for sulfur and get 0.75 mole, and we subtract each value with the smallest value present. So that would be 0.5. So for Fe, 0.5 minus 0.5 would be 0, and S with 0.75 minus 0.5 would be 0.25. So because Fe is 0, we know that it runs out first, and that would be our limiting reagent. And the mass of the excess reagent, because we know that it's sulfur, we take 0.25 mole from the equation before over 32.1 grams per mole, and we get 8 grams. So all we did is just rearrange the moles is equal to mass over molar mass equation and solved for mass. Moving on to yield. So percent yield is equal to actual yield over theoretical times 100%. And I have another example here. So what is the percent yield for a reaction in which 28 grams of Cu is produced by reacting 32.7 grams of zinc in excess CuSO4 solution? So the first thing that we want to do is write out the equation and make sure it's balanced. And then we want to calculate the theoretical yield for Cu. So that would be 32.7 grams of zinc over 65.4 grams per mole of zinc. So the 32 grams were given in the equation, and the 65 we can find on the periodic table. Because we have the balanced equation, we want to convert, like from the example before, we want to go from zinc and slowly convert it into Cu. So we would times that with 1 mole of Cu and 1 mole of zinc, and in this process we cancel out the units for grams and moles for both zinc, and we times that by 63.5 grams per mole for copper. So the 1 mole of copper times 63.5 grams per mole of copper, the moles and moles cancel out, and we're left with 31.8 grams of Cu. Now that we have our theoretical yield, we're going to write percent yield is equal to actual over theoretical times 100. We're going to plug in the values, and we get a final answer of 87.5%. And that's our final answer. Moving on to 4.6, we deal with ions. So we have more than one positive ions, where we have Fe2+, Fe3+, Cu+, and Cu2+. And then we have monatomics, polyatomics, and other polyatomic ions. Just make sure that you are familiar. This is super important. It does come up on the MCAT. You're able to differentiate Fe3+ from Fe2+ with the names and symbol and whatnot. So we're going to move to electrolytes. So, and that is containing equivalent of ions from molecules that dissociate in solution. The strength of an electrolyte depends on its degree of dissociation or solvation. So how well something dissolves in a solution or dissociates, those are your electrolytes. And that brings us to the end of chapter 4. Thank you for joining me. I'll see you for chapter 5. Take care.